So good morning all. This is Vivek Singhal. I am the co-founder and chief data scientist with CellStrat, and we run CellStrat AI Lab, which has now become one of the global AI research groups and very prominent globally. And we have about 160 AI researchers in our AI lab. Many of them are our students and AI interns. And we also have a Prime membership program for webinars. And we have the largest AI community in India today with about 15,000 members. So I welcome you all to the CellStrat AI Research Day today, which is a signature research showcase where our top researchers will present their papers. We are also creating a website on our portal which will showcase all of our papers presented in this today's research showcase as well as the prior one which happened a few months back. Okay, so I welcome you all once again. Let's get started here. Just a brief intro to our founding team here. Myself, Vivek Singhal, and Vishal is my co-founder. So I run the data science tech operations here, and Vishal runs our marketing and ops. And I have been a data scientist for the last few years, and before that I had a corporate career, and in between I ran many startups, which are shown here. Okay. So what is CellStrat? CellStrat is a leading AI startup, and we are engaged in advanced AI training and research, and we are also now engaged in product development for healthcare and pharma products using computer vision, natural language processing, etc. And we produce a lot of webinars in this space, which is pretty unmatched, in India at least, and even globally, we see we are quite trending. So we focus on vision, NLP, RL, etc. And we are in the midst of launching a lot of advanced courses as well for very state-of-the-art skilling in this domain. And we produce some of the most prolific, most advanced AI webinars, particularly originating from India. And we do have a global community of 15,000 members on our meetup group now. So our eventual vision is to create a unique AI, platform with which we'll be launching products and research for global marketplace. And in a new product team, which is hosted on Amazon Web Services Cloud platform, we hope to launch a series of advanced AI products with which we will be, addressing the global customers with health and pharma to begin with, and then increasingly other domains as well. So these are some of the POCs we have worked on, but I will let our papers speak for themselves today. I'm going to skip some of these slides. So these are some early photos from around August of 2018 when we started the physical AI lab meetup every Saturday in Bengaluru, and now we are fully online given the situation, and we have around 160 people in our AI lab and 90 people in our prime group and 15,000 overall community. So we are very grateful for the community ecosystem which has been created, and a lot of top AI researchers working with us for deep tech AI disruption. So I'll kind of end the intro there because we want to start our first paper almost immediately. If you have any questions before I hand over the mic to our first presenter today, please feel free to ask now. Okay, so I don't see any paper, any question, sorry. So in that case, let me invite our first presenter to today, for today, Shubha Manikarnike. And Shubha is our team lead for deep reinforcement learning research. And she is also the one who produced our advanced course in reinforcement learning. And she is truly a remarkable expert in this area. Let me make her the presenter. Shubha, good morning. How are you?
Yeah, hello. Thanks, Vivek. I hope my voice is clear.
Yes, yes. So our voice is clear so far, and kindly arrange a backup internet hotspot. And
Yes, sure.
with that logistics aside, over to you then.
Yes. Thanks, Vivek. So, hello, everybody, and welcome to this session today. My name is Shubha, and I am a researcher at CellStrat AI Lab with specialization in deep reinforcement learning. So today, for the first topic, we will be trying to understand how you can use reinforcement learning in this topic of supply chain optimization and also pricing optimization. So basically, this is based on a paper that was given sometime in 2018, where they tried out different RL algorithms for supply chain optimization. So let's take a look at one quick example on how you can define a Markov decision process for such kind of an environment and how you can use one of the RL algorithms to solve it. So that will be the agenda for today, agenda for this session. So we will start with a quick introduction on what is RL and how exactly is different, how exactly what do you understand by supply chain environments. And we will look at one specific environment and but try to model it as an MDP. That is, you will have to define the different states, actions, and rewards. So once you model it as an MDP, we will quickly spend some time in understanding the DDPG algorithm. And finally, we'll see how DDPG will solve your environment and we will analyze the results. There is a baseline as well. So we will compare the DDPG algorithm with the baseline. So I have written a detailed paper on this, which will be shared with you, and of course, it will be loaded on the CellStrat website. So for complete details, you can go through the paper and try to understand. And over here, I will try to give an high-level overview on what I'm trying to explain on this paper. So any questions, please feel free to ask, or you can also post it on chat. So with this, let's begin. So we know that reinforcement learning is basically, it is an agent which is interacting with your environment, and this agent has to perform correctly. It has to do different actions, and it gets feedback, which are rewards. So it has to do the actions according to the rewards which it gets. So basically, it has to learn based on the rewards which it gets. And we also know how this is different from, this is the third branch of machine learning, and how this is different from supervised learning and unsupervised learning. So what it receives from the environment is called as observation. It is slightly different from this definition of state, because state is basically a subset of observation. Observation is the complete whole superset, and state will, many times it might be a subset of your observation. It is just what the agent sees. So there could be other variables apart from what the agent sees, which could be termed as observation. So this is what reinforcement learning is about. Let us quickly look at a simple problem which you encounter in supply chain, which is called as inventory management. So you have orders which come in from customers, and you have your own program. So your own program over here, you can call it as the agent, and the role of this agent over here would be, it has to meet the customer's demands. So you have customer and you get the demand from customers, and the role of this agent is to meet the customer's demand. And in order to meet the demands of the customer, it has to get its supply from the basic factory warehouse, and it based on its demand, it has to place orders, and then you get the supplier or the basic factory warehouse produces, gives the supply, and this agent has to kind of perform, do some kind of optimization. That is, it has to understand what is the demand and how much it has to order, If it orders less, then it will not be able to fulfill requirements of the customer. So that would result in a loss. And if it orders more, it could incur more storage cost and other things, and hence then also it is a problem. So the role of this agent over here is to get the optimum, uh, is to kind of balance the demand and what it gets from the factory warehouse. So orders come in from the customer, and the agent's role is to meet the customer's demand. Uh, in order to meet the customer's demand, it has to ensure that it has enough supply. That is, it has in its storage capacity, it has enough stock in order to meet this particular demand. And obviously, it's not only not meeting the customer's demand is bad. So if the demand is high and you do not have enough stock, then that becomes bad, and this agent has to be penalized. So let's look at one specific example, and then we will try to understand how this can be modeled as an MDP. So you have a factory, and this factory has a warehouse. This factory has its own warehouse. This factory produces products, and these products are stored in the factory warehouse. And you have three distribution warehouses. So the products are shipped from the factory warehouse to the distribution warehouses, and this in turn sells it to customers or retail partners. So quickly, let's try to understand the different terms that we will be using in order to define our MDP. You have the production level at any given time step T. What is the quantity that your factory is producing? And the cost per unit. Let us assume that we are trying to produce one single product, and what is the cost per unit of production in the factory? And once it is produced, this comes into the factory warehouse. The factory warehouse has a stock level at a given time step T, that is, and it also has a maximum capacity. So there is a maximum capacity that it can store, the factory warehouse, and also there is the current quantity that it is currently holding. And apart from that, it also has a storage cost, uh, which is the cost for storing that many products in your factory warehouse. And from there, you have the three distribution warehouses. So for each of the distribution warehouses, A over here will be the number of products which are shipped from the factory warehouse to that particular distribution warehouse. Over at time step T, over here, the subscript J is J would mean different distribution warehouses. In this case, we have three distribution warehouses, so J will be 1 to 3. If you have multiple distribution warehouses, J increases accordingly. And Z over here, Z of superscript T is your transportation cost. So transportation cost to your different distribution warehouses will differ based on its distance from the factory warehouse. And each of these distribution warehouses has its own stock level at the current time. It has its own capacity, and there is a penalty cost involved, there is a storage cost involved, and there is also a demand. So at any given time step T, the demand could vary. And after that, you have the product price P. This product price P is the price at which this is sold to the customers. Uh, the penalty cost over here is in case the distribution warehouse is unable to meet the demands of the retail partner, that is, the demand was high and it did not have enough stock, then there is a penalty cost involved. So very briefly, this is how your environment is defined, and we have to model this environment as an MDP. So a quick thing about MDP is, in order to solve any reinforcement learning problem, it has to be modeled as an MDP. You have to define the reward that you get at every time step T, and you have a state vector. As I told previously, state is the subset of your observation. You have your state vector, and you have your actions. Actions is what you have to do, and once you perform this action, you move from one step to another. And also, when you perform an action, it is associated with a reward. So the key important things in order to model any given problem as an MDP is to define the reward, action, and state. So let's look at it. The reward over here is, this is the equation that is there for the reward, and this is clearly explained on the paper. However, I'll just quickly brief it over here. It considers the following things. It considers the revenue, total revenue generated, that is the price at which you are trying to sell, and times the demand, and you have the production cost. The second term is giving you the production cost, and the third term is giving you the storage cost. So storage cost will be storage at factory warehouse and storage at distribution warehouse, and there is a transportation cost which is involved to transport from factory warehouse to the different distribution warehouses. And also you have a fifth term which is the penalty. So as I told before, penalty is uh, penalties in case you are unable to meet the demand of the customer. That is, your stock is low and the demand was high. When you have a customer coming in, you do not have enough stock. Yeah, any questions over here? The next thing would be to define the state. So the state vector includes the current stock level at each of the distribution warehouses. So there is a maximum capacity that it can store, and also it also has a current stock level that it can store, and also the demand values. So the demand values for all of these warehouses are tracked for several previous time steps, because we assume that the demand varies across seasons. So there is a trend that is involved. At some seasons, the demand could be high, and at some seasons, the demand could be low. In order to track this trend, what we do is demand for different time steps is captured in your state space. So demand at every given time step is captured, and demand at every given time step would be the demand at that particular time step for different warehouses. So this is for warehouse 1 at time step T, what was the demand, so on till for warehouse W at time step T, what was the demand. And there is a state update rule that is happening. So once you perform any given action, the state moves on to the next state. So I would in order to write it as a reinforcement learning problem, you have a state, you have an action, and you have a reward. So for performing this action, you land up in the next state, and you get a reward for performing that action. And then in this next state, you perform another action. So when you perform this action, you move to the next state. So that is the state update or equation, or the state update rule that is there in order to get the next state. And actions are pretty simple. Actions would include, it is basically a vector where you're trying to ship from the factory warehouse to each of your distribution warehouses. So the quantity that has to be shipped from the factory warehouse to each of the distribution warehouses, the entire thing would form your action space, and each action would be, it would be a specific number. The demand over here is generated using, okay, first of all, the data set, or the data set that we are using over here is not a real data set that we are trying to capture from different warehouses. Rather, it is simulated using a code. So basic sine wave is used to capture the demand. And what you see over here, based on different time steps, the demand increases and decreases for the 3 different warehouses. Okay, there is a question on what is Markov decision process. So Markov decision process is the fundamental of reinforcement learning, where in order to apply an RL problem to any such environment. So we are trying to apply it to this supply chain environment. If you want to apply it to uh, a stock trading environment or any different thing, it has to be converted. to it has you will have to express it in a way on which you can apply an RL algorithm. So it is a fundamental, and it is a very huge topic by itself. So as a part of our RL course, it is covered in the second module, and there is a huge 2-hour webinar to explain how to model an environment as an MDP. But for this session, to give an overview, it is Markov decision process covers all about how exactly you model an environment so that you can apply any RL algorithm on that environment. So that is MDP, but then it has lot of intricacies within it, and it's very essential. It is the basic building block for you to understand RL. So I would recommend that since it's a huge 2-hour session all by itself, I would recommend that you visit the MDP session and different RL algorithms before we get over here.
Actually, this simulation is not too much off the mark. I mean, not too much off from reality, because in reality also we see seasonal demand pattern. So during
Yes,
festival season, the demand rises, then subsides. So it is a sine wave. So I think the simulation accurately reflects the correct actual behavior as well.
true. Okay, so now we have discussed the environment. I will spend a few minutes on trying to say what is DDPG. Again, I'm not going to go into the detail of DDPG. Recently, we covered this in one of the CellStrat webinars as a part of the course. So again, it is more than a 1-hour topic all by itself, and it has lot of prerequisites. So quickly we will try to understand what is DDPG, and we will move forward. So a question over here: how are you taking care of non-stationarity in demand? Uh, for now, it is it yes. For now, it is that demand has been generated using a function, but then if you are trying to consider real-time data, then you will have a different value for demand, and you will have to decide for what number of previous time steps you want to consider that into your state space. So over here, I'm more or less trying to explain how we can try to use an RL algorithm or try to model a supply chain environment into an MDP, and then how you can use an RL algorithm. But then, yes, if you want to enhance this or something like that, we will have to collect real data and consider all real-time scenarios. Um, so DDPG is the algorithm which is used for continuous action spaces. So to very briefly give you an idea to both of these topics, discrete action spaces is you're trying to predict a discrete set of values. We can kind of very vaguely relate it to classification. In classification, you just have 3 classes, and you're trying to say whether it's class 1, class 2, or class 3. These are discrete values. Whereas continuous prediction, you can relate it to regression, where you are having a value can be in a range of values. If you are predicting house prices, then house price can be between 100 and 1 lakh or whatever. So it is a range of values. So this you could call it as continuous variables, and this you could call it as discrete variables. And DDPG is an algorithm which we use for continuous value prediction. So basically, our action space, if you see, our action space is the number of units that you need to ship from the factory warehouse to the different distribution warehouses. So maybe you can ship 5 to the first distribution center and 100 to the second distribution center, and so on. So these are range of values, and these will not be discrete. So this is a continuous range, and hence we are using the DDPG algorithm. So DDPG is an extension of actor critic for continuous action spaces, and actor critic class of methods combine both in reinforcement learning. You have Q learning, or an extension of that, which is deep Q learning, which belongs to your Q learning family of algorithms. And then you have your policy gradients or policy gradient algorithm, which gives out the policy itself. So Q learning will approximate the value function and you learn based on improving the value, and policy gradient is trying to give out the policy itself using gradient ascent. So actor critic is that class of algorithms which combines the benefits of both, which is value based and policy based. It combines both of these things in one single neural network to derive the benefits of both. And DDPG is an extension of this actor critic algorithm, where you have two neural networks. One neural network will give out the value and the other neural network will give out the policy. And policy uses the value and value uses policy interchangeably, and it trains. Um, value uses the gradient descent algorithm. It performs based on gradient descent, and policy uses gradient ascent. For the policy gradient part of it, that is for this part of it, you have to your neural network has to come up with the optimal policy. So it takes in a state and it has to give out the correct action, and the goal of this entire neural network would be to maximize the total reward that we get. If you remember, we already defined reward from the previous time step. We already defined reward in our previous time step, and we have to maximize the reward. So that is the goal of your algorithm. And we do that using gradient ascent. In order to maximize your algorithm, we use the gradient ascent, where the weights of your neural network is updated based on this equation. Again, I'm just giving a very high level overview of this. You will have to in-depth go through the DDPG algorithm, and for that you will have to uh, be very comfortable with the basics of reinforcement learning. So for the actor critic algorithm, you have two neural networks. The critic neural network will determine your Q value, and your actor neural network will determine the policy. Both of these things will take the state as input. This gives out the Q value and this gives out the policy. And similar to our DQN, what we saw earlier, you will have target networks. You will have critic target and actor target networks, and you will also have a replay buffer over here. So for multiple number of episodes, what you do is you just pick random values from your replay buffer, and for multiple time steps you get the actor value from your actor neural network. You perform this action and you get a reward, and also you get a new state. You store this entire thing in your replay buffer, and then you calculate y. So y, this formula you are getting based on DQN. So this is again an elaborate formula for which you need a thorough understanding of DQN. DQN is based on the mean square error loss, where this is nothing but your mean square error loss, where you are trying to get your current Q value closer to your target Q value. So you take the difference of this and square, and you get your mean square error loss. And the policy part of it, the policy algorithm, is you get it by you get it by maximizing your Q. So you have to maximize Q based on the action that you get, and you update your target networks. You update your target networks based on this policy called as soft update. I understand that if you're not familiar with RL, you wouldn't have got anything out of what I explained about DDPG, but due to time constraints, I cannot take much time to explain about DDPG. So I hope you kind of have an idea of what it is. We will move ahead. So I will pause here for a minute. If you have any questions, please do ask.
Yeah, as Shobha said, this probably needs RL expertise, which is quite a sophisticated subject in itself. But the interesting part about this paper is how this RL technique is being applied to inventory management problem and optimizing just-in-time inventory between different warehouses. Because as you know, if you are from manufacturing or supply chain world, the hold cost of inventory is very high, and if you have less inventory, you lose business. So just-in-time inventory is absolutely a massive application of this kind of algorithms. So that is, I think, the point of this paper. The algo itself is quite complex. Unless we have an RL background, it's hard to understand. So that's fine.
Okay, let's move on. So the results have been put over here, and this was the baseline that I was talking about. I have not gone in depth into the baseline, but this baseline is explained on the paper. So once the paper is uploaded on CellStrat website, please do feel free to go through how the baseline is calculated. So briefly, the baseline is uh, it is what it does is it for any given distribution warehouse, if the quantity or the current stock level falls below some number, let's say as some threshold. So if it is below some threshold S, then they order Q more quantities from the factory distribution warehouse. So this does not take anything into consideration. It just checks what is the current stock level in the current distribution warehouse. And if it is less than a threshold, then go ahead and order some more or Q more values from your factory distribution warehouse. So this is just not based on any AI or anything, just a simple policy that was used as a baseline. And by using this policy as a baseline, they were able to get a cumulative profit of 6871. And then by using DDPG, the cumulative profit they were able to achieve significantly higher profit. So for different time steps, this graph records the cumulative profit and the quantity that has to be shipped to different warehouses, what was the quantity that has to be produced, and the stock that is being stored in different warehouses, and also the stock that is shared on the factory. So it is also classified as the reward that you get, and action, as we saw before, action would be what are the quantities that we are trying to ship to different warehouses, distribution warehouses from the factory warehouse. And state would be uh, the demand and also the current stock levels at different warehouses.
Yeah, from my supply chain days, we used to call this short stock. So whenever it reaches the short stock level, it triggers a inventory order in a warehouse or a store.
Mhm. Um, so I will, the code is okay. On the paper, briefly on the paper, we are trying to explain what is the inventory ordering problem that we have, and the environment is being described with different with the different terminology or notations that we are using for different things on the environment. And this we kind of understood clearly while during this session. And we also understood how the reward is defined and the state is defined and also the actions are defined. And the demand over here is simulated, as we told, based on a sine wave. Based on this formula, the demand is auto generated. And this is the baseline that I was talking about. So if this is a simple baseline just to test how our algorithm is performing. So if you are able to get, if it reaches below certain threshold S, then uh, order Q more products is the simple baseline that we have. And after that, you have your DDPG algorithm. So as I told, the 10th module in the RL course is explaining the DDPG algorithm more thoroughly with the complete code implementation. And the DDPG algorithm, as this is as taken from the DDPG paper itself. So for continuous control, the algorithm which was defined in the original paper, and then the results have been marked. So please do go through this paper and we can kind of go through the code. So I will go through the code at a high level, and a couple of things that I want to mention over here is uh, yeah, the state action reward, all those things are implemented. But then in this code there is a package called as, there is a library called as rlib. So this is an open source library which was given by I guess the UC Berkeley University from London. So they have kind of automated this rlib library, includes most of these algorithms are implemented. Like you have the DDPG algorithm, PPO, and normal policy gradient, VPG, and all of these algorithms are available as APIs to us. And the code over here, this code was implemented in the paper, and I'm just reviewing the code which was implemented in the paper. So this code uses that rlib library. But then as a part of our DDPG session, we have kind of completely written the entire code in PyTorch. So we have completely implemented the DDPG algorithm in PyTorch, and we have a hands-on code demo for that. But for the sake of this exercise or this paper, the code over here on this paper is written from the rlib library. I will briefly, at a high level, I'll go through what the different functions are using. So state is to define the state. As we saw, state consists of the stock levels at different warehouses, and also the stock level at the factory warehouse. And action is just 1 minute, please. Yeah, action is what we are trying to ship from each of those, from the factory warehouse to each of the distribution warehouses. And you have your supply chain environment, which is created. The demand, as I told before, is auto-generated using the formula we just saw. And you have a step function over here. So step function will perform that action, and it will calculate your reward, and it will move on to the next state. So the demand, as we saw previously, is depicted, was created using a predefined function using that formula, and it is generated using a graph. Some functions were written for visualization, and your baseline policy function, which just orders Q values if it is false less than the threshold S, is written over here. And finally, when we come to our DDPG algorithm is written using rlib, and all that you have to do over here is pass a few parameters. You have to just pass a few parameters and call your ddpg.trainer, and based on the neural network that you have created and different parameters that were passed, it automatically trains and gives out the result. So this result, we already saw it on our PPT. So if you have any questions, please do ask.
So, friends, any questions?
What is SKU? I am sorry, I'm not able to get.
So what I'm trying to ask is this paper implemented for just only one SKU? SKU is a stock keeping unit. Like say you have Surf Excel. So there are many
Okay.
Surf Excels kind of. So a 10 gram,
I guess
1 kg.
for one product and three distribution centers.
Okay.
Yeah, actually, this can be extended quite significantly, not only over
Yes.
thousands of products, but also, within a factory, there are multiple assembly lines. So different assembly lines produce different SKU products. So even that variation can be implemented. We had a sort of a client talking to us who wanted to do this and with RL and with multiple SKUs and multiple factories, multiple warehouses, and multiple store distribution network across the country. So it can become
Mhm.
quite a elaborate, problem statement. And this is actually just the beginning of what is possible actually.
Okay.
Because even within a factory, different you have different resource management, like the different assembly lines, and they have their own cost factor. So you decide what time of the day which assembly line has to run and what products have to be shipped out like that.
Okay. Thank you.
I mean, outside of RL, we really don't know how else would you do this. There are traditional optimization techniques the supply chain industry has been using, but they are very suboptimal, and RL is able to solve for a lot of that now. Other questions, audience? Okay, so thanks a lot, Shubha. Excellent paper. And this paper PDF is available, and it will also be hosted on our CellStrat research portal soon. So if you need a copy of this paper PDF, reach out to us. We'll be happy to mail it to you. And now next, thanks a lot, Shubha. Next, I'll be
Thanks,
handing
Vivek.
over the. Thank you, Shubha. Excellent paper. And next, we'll be inviting Nikhil Narayan, the next presenter for today. Thank you once again. So, Nikhil, good morning. How are you?
Good morning, Vivek. Am I audible?
Yes, yes, all good. So then over to you whenever you're ready.
Yeah, can you hear me?
Yes, yes, we can hear you.
Okay, super. So I'll get started then. Good morning, all. Today I have written a review paper on SimCLR, a simple framework for contrastive learning of visual representation, and I'll be taking you through what actually SimCLR is doing and what are the results which came out of SimCLR. So this is an self-supervised learning framework which was developed by research scientists at Google Brain, and a paper was published early this year. So in today's contents, we'll see what are the limitations of supervised learning, what is self-supervised learning, and the contrastive learning, and which is SimCLR is based on contrastive learning. Then we'll look at the SimCLR framework and the results from SimCLR. So we know that a lot of state-of-the-art models have come out of supervised learning, and there are many supervised models being deployed in production. But supervised learning models or supervised learning in general comes with fair share of limitations. So supervised learning, essentially solves a given task efficiently only provided that there is enough labeled data. But collecting large amount of labeled data is expensive, and it's very hard to annotate data and make it labeled. So if I draw a typical 2x2 matrix with cost of collecting data on the x-axis and availability of data on the y-axis, you will see supervised learning falling in the negative quadrant solely because The availability of labeled data is very less in most of the use cases, and annotating unlabeled data for and making it labeled is a slightly expensive procedure and takes a lot of time. And in contrast, you will find that supervised learning falls into the positive quadrant solely because you don't need labeled data for unsupervised learning, and hence the data is available in large quantity. That is, the unlabeled data is available in large quantity in the internet, so you can easily get hold of them. So the cost is also less. Then the question is, why are we not seeing most of or more of these unsupervised models compared to supervised models? The reason is it is slightly tricky to train unsupervised models with labeled data, sorry, with unlabeled data, and historically we have seen that unsupervised models performance is relatively low compared to supervised learning models. So the question now is, let's say I have a large amount of data. Okay, I have a large amount of data available, and from this data only a subset of data is labeled. Okay, and the rest is unlabeled. So the question what is asked in this paper is, can we make use of both of these together, not solely depending on one of these, and achieve what a supervised learning model can achieve? So only with a small subset of labeled data and with large amount of unlabeled data can we achieve the same performance as that of a supervised learning model. And that is what this paper is answering. And to answer that question, we have the self-supervised learning algorithms. So self-supervised learning is a subset of unsupervised learning, you can say. So in self-supervised learning, what happens is that it tends to train an unsupervised or unlabeled data set in a supervised manner. So you can do this by predicting only a subset of information from a given data set. So as you see in this image, you can see that if this is the whole data set, you're trying to predict the future from the past, or future from the recent past, or past from the present, or top in the present you are trying to predict the top from the bottom. This you can relate it to, say, videos. So if you have a video, for a certain amount of time, shown the uh, previous say for a time frame, or a given time frame, can it predict the future time frame? you know those kind of things fall under self-supervised learning tasks. Or in case of images, if I have a particular image and I crop out a part of it, can the model correctly identify whether this part is part of this uh, small portion of the image is part of this image or not? So uh, I think you can also relate this to NLP. So if you have a certain long sentence, if given only a first portion of the sentence, can it predict the other part of the sentence? So these kind of things are part of what is called a self-supervised learning. So in self-supervised learning, the tasks are known as pretext or auxiliary tasks. So this is not your main goal or end goal. So what you're doing here is that in case of image data, you're trying to learn an intermediate representation of that image. So once you learn that intermediate representation, you can use that representation for other downstream tasks such as classification or segmentation. So the analogy what I can give here is, uh, let's say, like a pre-trained model. You have a pre-trained model, so you are going to use this pre-trained model to solve your main problem. Or another analogy could be like initialization of weight. So if you get the weights initialized in a correct manner, you have a lot of advantage in actually doing your main task. So in order to do this, we don't need labeled data. We can make use of unlabeled data and define certain pretext tasks so that the model can learn these intermediate representation well, such that it can be further useful or um, more efficient in performing the downstream tasks such as classification or segmentation. So any questions, please do put it in chat. Okay, so there are a lot of pretext tasks which can be used in self-supervised learning. So I'm today we'll be just talking in terms of image-based data. So if you have image-based data, then these are your uh, pretext task, like for example distortion. So here what you're doing is I have an original image and you are applying random transformations on this original image and producing a set of transformed images. Now the pretext task would be to classify all these new transformed images as this class similar to what is being here. So in this case it's a deer with a lot of transformation. So all this should be classified as belonging to this image. So for this, you don't need labeling of data, right? You just need this one image and its corresponding transformation, and the objective of that model would be to just say if this image belongs to this one or not. And second one is missing patches. So let's say I have what I was explaining previously. If I have an whole image and I just want to know whether a portion of that image belongs to this whole image or not. So that could be another pretext task. Then you have something called rotation. So if I take an image X and I rotate it at certain angles, the model has to predict what is the rotation. Is it 0 degree, 30 degree, 40 degree, etc. So that is another pretext task. And there are other popular pretext tasks as well. So for example, something called colorization. So if I give a grayscale image, will it be able to color that grayscale image representing the reality or not? Then you have something called as denoising autoencoder. So if you have an image with a lot of noise, or then is it able to denoise that image or not? So that is another pretext task. Then you have something called as context encoder and bidirectional GANs, which are also used to frame a pretext task. So when you are framing a pretext task, the model used for this pretext task is not your end model. Remember that. It is just to ensure that it learns the intermediate representation or the latent space well enough that so that we can use that for our downstream task, which would be our actual task. So since there are a lot of pretext tasks available, it's important that you choose the correct pretext task depending on what downstream task you are going to perform. Then you have something called as contrastive learning. So contrastive learning is also a pretext task. Here what you are learning the representation by making the model uh, or by enforcing the model to identify similar elements and push away the dissimilar elements as shown here. So what you have here is a dog and its augmentation, and a chair and its augmentation. So the model has to attract the augmentations together or give a positive results and penalize when it is classifying dog as chair or the other way around. So if the images are of from the same source, you don't penalize it, but if it is the other way around, you penalize it with the loss function. So SimCLR is based on this contrastive learning approach, and it learns the intermediate representation using this contrastive method. So SimCLR and most of these self-supervised learning approaches are largely still in research field, but SimCLR has promised the results from SimCLR is very promising. So the success of SimCLR is largely due to three factors: the data augmentation, its model architecture, and its loss function. So it uses unlabeled images, and it tries to use heavy data augmentation to get the desired results. So let us go through each of these three components of SimCLR to understand how SimCLR works better. Yeah, so when you give an input image in the data augmentation process, it creates two correlated copies of it by applying random data augmentation. So as you can see here, this is the original image and you have a set of data augmentation applied. So it will create, for each image, it will create two set of transformations. So let's call it T and T dash. If this is the original image, for this original image, it will apply two separate transformation, T and T dash. There are a lot of transformations which they tried out, and they figured out that random crop and resize, random color distortion, and random Gaussian blur works better. So in the research paper, they have applied only these three uh, data augmentation operators. So since there is certain amount of randomness in each of this operation, these two images will be visually different. So so apart from these original images and its transformation, it will, in when you feed in the batches, it will combine the negatives along with the original image. So the negatives are all the images apart from the image itself and its transformation. So any questions? Okay, no questions until now. So the model architecture is very simple and straightforward, and that's also the reason why it's called simple framework. So what it uses is a ResNet 50 as the main coordinate backbone. You can use any convolutional network, but the research paper has used ResNet 50. So this ResNet 50 receives an augmented image of shape 224 cross 224 and outputs a 2048 dimensional embedding vector H. So this is your, so let's say you have an original image and you try to pass two set of images. Then you apply ResNet on top of it to get an embedding of it. So that is H. Once you get an embedding, you apply a projection head onto that embedding. So this is called as a projection head. So projection head is nothing but a multi-layer perceptron with two dense layer. Both layers have the same dimension as the embedding vector, that is 2048, with a hidden layer, and the hidden layer as a nonlinear activation function, which is the ReLU. So once you pass the images, it goes to ResNet, produce this intermediate representation. Then you use this intermediate representation and pass it again to a multi-layer perceptron to get this embedding Z. So you get two, since you're passing two images, you get two embeddings, and then you try to see how similar these two images are. So to find the similarity, you use cosine similarity. So once the cosine similarity is found out, you can use the loss function on these similarity score. Uh, so on this similarity score, yeah. So I see a question. Yeah. So SimCLR, what is the difference between SimCLR and Siamese network? Yeah, that's a good question. So you see, there are a couple of differences. One thing is in Siamese network, you pass in two different images and not the augmented images of it, right? And then you try to find the similarity between the intermediate, the representation. And we stop at this point. In here, you again pass it through the projection head and find the similarity score, and then you use a completely different loss function. So the loss function is completely along with the projection head, the loss function is also completely different compared to your Siamese network. Yeah, so coming to the loss function, the loss function is known as NT-exent, which is nothing but normalized temperature scaled cross entropy loss. The paper refers to uh, gives this name as NT-exent, but in general it is called as noise contrastive estimator, the NCE. And in the original paper, you might find the equation slightly different, but both these equations would typically do the same job. So here, what you have is a similar sim is nothing but your similarity function. So this is your cosine function. So you find the cosine similarity of the Z representation of the original image and the transformed image, and then pass it and do the exponential of it, and then you do the same for its negative counterparts. So x plus is a data point similar to the input x, and usually x plus is the result of some transformation in x, and similarly x minus are examples dissimilar to x. So for each positive pair, we'll have a set of k negatives. So for each in the batch, when you give that mini batch, for each set of positive pair, you'll have k set of negatives. So these k set of negatives are nothing but all the images apart from the original image and its transformations. And G is nothing but your projection head. That is nothing but another MLP, multi-layer perceptron. So this is the loss functions which is used, and when they used this model, what they found out is that these representations can be much more useful for performing downstream tasks with less number of labeled data set. Or you can train this whole model with unlabeled data set, use this representation and train it with a small amount of labeled data set to get the same performance as that of your supervised learning models. So if you see the SimCLR results, it's actually very promising. So again, once you train this model, you don't need to use the G part of it. You can remove the projection head and use just the representation. So what they did was they used this representation and passed it on to a linear classifier and trained on this ImageNet data set. They found that it achieves 76.5% top one accuracy, matching the performance of a supervised ResNet 50. And when they fine-tuned with just 1% of labeled data set, they achieved 85.8% top 5 accuracy, and it outperformed AlexNet with 100x fewer labels. So this is something very powerful, a simple framework, but its efficiency is there to see, and this is something which is going to be predominant in coming days, that you will see people using this kind of framework for pre-training, where you have very limited amount of labeled data, and then using the intermediate representations to perform the downstream tasks. So yeah, so what next? So what I'm currently working is on SimCLR on medical images. So again, in medical images, you have a limited amount of labeled data. So what I'm trying to see is that uh, if we pass medical images onto SimCLR architecture, how these intermediate representation looks like, and can we then use these intermediate representation for our actual task. So for medical images, definitely one thing is that we cannot make use of the same augmentation what is used here, because I think medical images are more sensitive to what transformation you apply to it, and that will have a huge impact on the intermediate representation which will be coming out of that. So this is something which I'm working on, and I'm hopeful that I'll be able to present the results maybe by end of this month. And yeah, and next I also have a webinar which is again based on the SimCLR, where you are doing anomaly detection or out of distribution detection, and it's on 15th of December, where I'll be taking you through possibly a code demo as well. Sorry, for today I don't have a code demo, but on 15th December I'll also have a code demo based on contrastive learning, where we'll be doing anomaly detection using contrastive learning. So any questions you can ask?
So very quickly, Nikhil, can you summarize this solution in sort of one or two lines? Essentially, you are augmenting an image and creating two augmented images, and you are comparing them
Yeah.
to do what? You are comparing two augmented images. What does that achieve? Just to summarize.
So when you are what you are essentially telling is that when you are comparing, you're trying to minimize that loss after comparing. So when you do that, the intermediate representations of those images, uh, the latent space would be much better. So when I take this latent space and uh, perform a dimensionality reduction on this intermediate representation, you can see that that would be better classified.
So what is the purpose of applying MLP on top of the ResNet embedding?
Yeah, so what they found, see, actually you can just use this H as well and do the same phenomenon. But what they found out is when you have an additional MLP layer, these intermediate representations get better compared to what is coming out of ResNet. So you are actually, when you have an additional layer, you are actually fine tuning this nonlinear layer to produce much better intermediate representation.
So you are doing further feature discovery using
Yeah,
MLP on top
yeah,
of ResNet embedding.
yeah, yeah.
And once you
So
minimize those two, you are able to do some of those labeling tasks or colorization tasks and so forth. Now patch filling.
yes, so patch filling
Mm.
and everything is a pretext task. So you use those pretext tasks to produce this intermediate representation, or the latent space, what we call it. So once we have this latent space, okay, I can tell you this way. Let's put it this way. So when you produce a better latent space, the model has somehow learned to classify these images better based on just agreement whether these two images are similar or not. You understanding? For example, I uh, for example, if I pass a dog and a cat, it will try to push them away based on the loss function, right? And if I pass a dog and its augmented image, it will try to pull it close together. So essentially what you're doing is, without providing the labels, it is trying to classify based on just comparing the images. So now the intermediate representation would have already somehow classified it without any labels at all. Now you can use this intermediate representation and perform a supervised learning on it to get much higher efficiency with limited amount of data.
Okay, so since we are missing Y label, you augment the image into two images
Yeah,
and you
yeah,
compare them with each other.
yeah. So without label itself, it is trying to classify it,
Hmm.
and that is seen in this intermediate representations. But this may not be the perfect classification. So that's why we need to take this part of the model and retrain it using a limited amount of limited amount of data, labeled data. So that is what it's saying here. When they fine-tuned it only with 1% of labeled data, it achieved 85.8% accuracy and outperforming AlexNet with 100x fewer labels.
Okay.
Yeah, so there's another question. How does the choice of data augmentation impact the learning? So in SimCLR, augmentation is very, very crucial. So they have done a lot of experiments and they found out that these three work particularly well. And this random color distortion for pretest task is most crucial. And the same thing when you do it for supervised learning, you might find that something like random color distortion might give yield in poor results. But for pretext tasks like this, the random color distortion proved to be very crucial and helpful. So again, as I was telling you, that you cannot use a similar augmentation for medical images, because if you do, let's say, color distortion on a X-ray image, then maybe the intermediate representation will not be well classified. So the choice of data augmentation is crucial, but that is also you need to experiment it out.
So once I get the H, a good H is the hidden representation. Once I get a
Hmm.
good H, you will be doing a limited supervised training on it to classify it.
Yes, yes,
So
exactly.
the theory here is that the H now is a very, very strong hidden vector for the image. Am I
Yes,
right?
yeah, yes, very
Got it.
strong latent space. And
So
also the
that
weights
this
would have
H is
been,
better than the H achieved just with a basic autoencoder.
yeah, yeah,
Okay.
true.
Okay, got it. So
And also
essentially,
the
you're trying to
weights,
get the hidden representation more perfect, and then you run a
correct.
limited classification on it, and you are able to train a good classifier using limited labeled images.
Yes, correct,
Okay.
correct, absolutely right. Also the weights of that model, the resonant model would have now been better, right? It would have been better initialized. So when you train with limited amount of supervised data, since the weights are already better initialized, that also will lead to good results in supervised learning with limited data. So there's a question that how do you choose the data augmentations? uh, it has to come from experimentation, but in most of the cases you can use whatever is used here, the random crop and resize, random color distortion, and random Gaussian blur. This should work for most of the data set. But my only concern is with respect to medical images. Maybe medical images will not work with this data augmentation, and that's what I'm uh, trying to experiment with. And once I have the results, I'll try to present. And the next question is, in case of rotated images, is the goal to identify the rotation? Yes, the goal is to identify the what is the angle of rotation. So are there any other questions? So I also have this paper, which is a little more in depth, but uh, it gives the same content of what I've delivered now. So there are one point I want to make is there are other self-supervised learning algorithms which has come previously. The popular ones are MOCO, Momentum Contrastive, and PIRL, Pretext Invariant Represent Learning. So here in MOCO and PIRL, what the disadvantage was that the model was not as simple and straightforward as this. They had something called as a memory bank. So this memory bank used to store all the negatives images, the negative paired images, and then it used to run through this used to run through this memory bank to produce this kind of maximum agreement. So it had this additional component called as memory bank. But what SimCLR did was that with the help of this unique data augmentation or data heavy data augmentation, they tried to remove this memory bank, and whatever images which were not its if you had an original image and you had its two transformation, let's say t and t dash up, and if you had to make a pair, a negative pair, apart from these three, every other images would have been as a negative pair. So you didn't have to have a separate negative pair data set stored in a memory bank. So that is one of the biggest advantage of SimCLR. So, and you
See
can
that
also see.
formula you the
Mhm.
formula you showed looks like softmax formula, right? So
Yeah, yeah, it's a
e to the
cross
power,
entropy loss. Yeah,
yeah, this categorical cross entropy, what we use in multi-class softmax classification. A somewhat
yes,
similar formula is being used, yes.
yes. And another thing in this loss function, what it's not there is in the paper you will find that they have added a variable t or a parameter t. T is called as a temperature, okay, and this is a parameter, hyperparameter. This is just to used to normalize what is coming out of this cosine similarity. So in the paper they have used value t equal to 0.5. So are there any other questions?
So friends, Nikhil will be presenting an application of this technique for anomaly detection in the coming week, a sort of a dedicated webinar which is listed here. So applying this technique for the purpose of anomaly detection. So
Yeah,
that will be kind of an application webinar of this particular algo.
yeah. And probably we can also use this for out of distribution detection for our medical images. And that's also something which I am thinking of. And yeah,
Correct. See,
where
this also
instead of,
compares with things, few shot learning, right? Few shot learning also
yeah,
enables
yeah, the
limited
Siamese.
labels. Yeah,
So yeah, so the only difference between Siamese or one-shot learning compared to this is you have an additional MLP, and the loss function is different. What you're using. So yeah, so as I was telling that you can also use this for out of distribution detection, which will be covered here, and this should perform better than your not normal autoencoders, as far my guess is concerned. So we can try this as well for our
hmm
out of distribution detection for medical images.
right. So for any particular problem statement, such as out of distribution, we continue to find newer algos which can improve on the existing techniques. So one has to constantly evolve the products so that one is more state of the art. So it's a moving target. This paper is from July, I think, from Google Brain, right? SimCLR, July of this year, pretty recent. So any questions, audience? So this paper is also available as a downloadable PDF. It's a review paper on the original SimCLR and the related papers, and you can get access to it by contacting us. And we'll be also posting it on a research portal in the coming week. Any other questions, audience, for Nikhil here? Okay, so thanks a lot, Nikhil. A very excellent research done here, and look forward to having your paper on the portal soon. Uh, Audience can always get it as a downloadable PDF. Thank you once again, Nikhil. And
Yeah, thank you.
okay, so let me now invite our third paper presenter for today, Indrajit Singh. Indrajit is our team lead for NLP research and also the creator of our vast NLP course, a very rich course. So I'll be making Indrajit the presenter now. Hi Indrajit, good morning. How's it going?
Hi Vivek.
So you ready?
Yeah, Vivek, I'm ready.
Okay, so over to you whenever you can start.
Sure. So hi everyone. I'm Indrajit Singh, and I'm an NLP researcher and scientist at CellStrat. And I have been mostly exploring the problems associated with natural language processing um, uh, and the advanced side of NLP. So in NLP domain, I mean, you might have heard about BERT, and there are many other algorithms that comes in today, right? So these are the popular algorithms that's been used, and I mean, if we I mean these are not just algorithms, I would say, you know, just to be in the research paper, and now it's time that we see these algorithms as an having a commercial use, and in even in production systems that we are using a lot of applications built from scratch using BERT or AilBERT or even the variants of BERT. So over the times, even Google has recognized, and as you know, this BERT has been developed by Google, and Google has recognized BERT as in one of the algorithms to improve their search engines, and they see that there has been a 10% improvement over the searches earlier, and it can really boost the search types and also the results that comes in from the user. So with that idea, I am presenting one of the aspect of these BERT algorithm, and how this can change the way we get the search results and the way a search engine works. So, and also the intent of these particular paper is to um, make most of the people understand it's not just the Google search engine, but any search engine today that you would like to build, and that could be built using BERT, and that's definitely a huge advantage in the search queries and the results that we get. Okay, so as an abstract of this paper, I would like to say that, I mean, you know, the search for human history has never been an easy task. I mean, uh, it's a problem to be solved every day, and it's a problem would be there until humanity is there, because the search started from the beginning, when there's an you know when the humanity begins in this world, right? So people searched for food, people searched for different like say for how to lit fire, or they search for will, and then so on, right? So and we came to this information age. But apart from, I mean, internet or what's available in the web, right, I mean, the way we search things is never been changed. I mean, we always want to look for, or we ask people that, hey, I'm looking for this particular object, or hey, how do we get the best doctor in this particular city? We probably put it in a group, or we probably ask someone, or we probably Google it. But do you, I mean, you always have an experience that you do not really get what you are looking for always, right? And you most of the cases, you get something from Google, which probably give you some direction, but it's not the right answer, right? So believe me, Google search engines, I mean, which is I'm comparing because that's the biggest and largest search engines available today in the world, right? So they still have a lot of problems to be solved every day, and it's like, I mean, I can give you one example. Like they have 40 million, or I would say that 40% of the web pages as a spam, or with full of ads or not relevant to the search. So how can we deal with such kind of problems that's available today, right? So again, I mean, this is one of the aspects of it, and there are challenges like search. You when we search through I mean, in Google search engine, let's say you throw a question like what kind of battery fits well with water heaters, right? You may get some suggestions, but it may be there are no answers, or might be there are answers hidden somewhere, right? So so how BERT actually improves that, we'll talk about that in our later section. But let's understand the problem statement, and this is how, I mean, we can think of solving the problem that's available today, right? So as an introduction, I would say the topic is basically, according to Google search engine experts, there are every day almost 15% of search queries submitted as new. So there are new search queries to be solved, and let's say there are old queries that has to be improved upon, right? So from the history that of search engines, they started working with TF-IDF and cosine similarities, right? That's not been changed a lot. I mean, we'll see how that's not much difference with BERT and the variants of BERT. Okay, so the question here comes is that can we imagine a world of perfect search results? Can BERT or its variants make the search engines better? Of course it will make the search engine better, but we cannot really have perfect search engines, because the amount of data, amount of web pages, the amount of resources that's being dumped into web is not controllable, right? So that cannot be curated, that cannot be like having we cannot have a rule to put something which is not relevant. I mean, people always find a way. People are smart and they find a different algorithm to put beat Google or Google search engine, right? So this is a never-ending problem to be solved. So that's a big question here. And the answer is through BERT. I mean, though BERT has added more power to search engines, there's still a bigger problem to be solved, and users are looking for more meaningful and specific answers to their queries, which is the toughest or hardest problem to solve. So let's say broader search queries, like let's say you search for a football club in India or in world, right? The best football club, you will get a lot of answers, and you probably see you probably get the best one from the search. But if you search for like where do I get tuna fish in probably let's say in Chandni market, right? So you probably get some rubbish answers, so which is really a problem, and it has to be solved in better way. Probably there are no good, I would say, data. There is no good results or good information available in the web, right? I see there is a question. There is a suggestion here. I mean, a very good search engine based on NLU and mathematics is Wolfram Alpha. Yeah, I agree. This is a really good one. But so these are huge trade-offs. I mean, I see that people are building good search engines today, but let's say Google has huge amount of data and over web, and they have they have data centers, right? You need to have a faster processing engines and faster response time. Like it should be in in like fraction of seconds, right? You get a response. So you, let's say you just try something, search something, you get in probably 0.06 milliseconds or 0.06 seconds or something. Even let's say some results are like 1 second, right? So how does it, like, make more and more information or in the web, and you get what you want, correct? So that is something, a very bigger problem to be solved, and narrow questions are much more complex than the broader questions, isn't it? So the objective is like this small paper, to look, that looks at the trade-offs of the of how BERT can make a difference in the search world. So let's say, I'll take one example of the complexity of search, and the complexity of a simple search based on users' requirement. For example, that use, I'm sorry, this image is not very much visible, but I'll explain it. So when we search for a query, Google looks for the relevance of the query and many other parameters such as meaning of your query, relevance of the web pages, quality of the content, usability of web pages, and context settings, right? So like let's say you, right, so let's say you are located in Bangalore, or you are located in some other part of the world, and so if the two users are searching for same thing, they might see a different result. So this is basically the location or context based search and the relevance of their queries, right? So I may not expect similar kind of results as another user in the other part of the world is looking for, right? So so let's say a search engine query that is more into knowing the intent of the user, knowing the the meaning of what they are looking for, right? So that is a bigger problem to be solved, and we have some existing problems with the queries that we see. So I'll take one example that I quickly searched before preparing this paper. So you see this, I searched like best available baby food in Goa, right? So you see that it shows First Cry store.
Mm, I cannot hear. Maybe Indrajit lost power. Yeah.
All right. So as I was talking about the search of the user, and the based on their location and the way they search, that varies, right? So I might search in different way. I'm a lame user of Google. Let's say I just want to get some information about the baby food, right? And I'll just type it like the best baby food available in Goa, and I might get this First Cry store, correct? So this could not be so urgent, or this could not be so much like, have to have a right information, but there could be some specific queries where we need to have a specific answers, right? So there are blogs already written, and let's say about baby food, and that talks about the top baby food or best baby food, based on the context of the user, is really really tough to get. So we have these problems to be solved yet, as a search engine, and Google still doesn't do that. Okay. Again, like if you search, let's say, best baby food in Bangalore, you might see a different result. if you try it, you will see that it doesn't show first cry, or it shows some other stores, store names, right? So which is again, that's something that we need to look at. Okay. All right. So at this, like, in this paper, I broadly spoke about BERT and the and their variants. So though I did not take all the variants, there are many variants of BERT today. But one of the paper that was published in 2000, I mean this year basically. So that's an overall idea of twin BERT, and that basically takes the same thing how BERT takes as an input, but there is a little difference that they make in their objective. So let's understand that how BERT actually takes an input, right? So normally, with BERT we feed in with a we use a transformer, right? And a transformer is basically consist of an encoder and decoder architecture. So in BERT, when we have an encoder decoder architecture, we use a pre-trained model, right? So because all of these are basically a variant of pre-trained language models, right? In BERT also we use a pre-trained language model, and we feed in the data. We have an embedded data, and we have a positional embedding being used, and then we use multi-head attention, which is in short, a multi-head attention takes a query and a key, and it multiplies that query and key and gives you a score, and that score goes as an attention score, and we take the highest score and then find the neighbor of that head, and then we see that what are more relevant to that particular that particular word or sentence, correct? So this is how we progress, and we see in a document or in a corpus. So a corpus is a collection of multiple documents. So in a document, let's say we go for a paragraph, and we see the most applicable paragraph or sentence that is relevant to the query, and you give the output. Okay, so that's how BERT works. So before the invention of like BERT, if you know, like all the search engines used to work in based on retrieval systems, and that has this TF-IDF formula, right? So we have these based on the term frequency and the document frequency, and we get these like, let's say user searches in a browser, and he hits an query like, how do I fly to Mumbai, right? So it basically looks for all the terms available in the documents, and it gets the term frequency from those documents, and it sees that which document is having those terms that the search is looking for, and then it basically calculates the TF-IDF value. And once we have the TF-IDF, we calculate the cosine similarity of the document and the query that's been searched. So the document that is highest match with the query that is given as an input by the user will get those documents in a ranked order. So the top ranked document will have in your search will be shown in the top, right? So that's how TF-IDF and cosine similarity worked. And in BERT also we do the same thing, but we call it a transformer. In transformer we have multi-head attention, and multi-head attention takes an query and a key, and then it calculates a score, which is again finds its neighbor, and it calculates the score for the neighbor, and so on. So it basically it does it in a different way, but ultimately in mathematical way it is the same thing that been performed. There is a difference in how we take the input of the sentences. Like we have these sentence, let's say the beginning of the sentence and the end of the sentence. So we call it like sequence, CLS and EOS, right? So all of these are incorporated with BERT. Now, um, apart from these things, like how do we discover a like a search query and or a uh, relevant query and the output of that particular query, right? So let's look at these. Like if you're taking example of this TF-IDF, and then we calculate the rank of the documents in the highest to lowest order, and based on the query and the document similarity, that cosine similarity gives the highest score of the document having best match and lowest score for the worst match. So if being cosine similarity between 0 to 1, or the cost function -1 to 1, let's say we use the softmax function to basically I mean basically make them as in between 0 to 1 in the positive segment. So we get that value, and then we see that so the query and key is being calculated through this particular score, and it gives you the rank of those documents again, right? So so this query key, as you see, and the score, this comes from the transformer architecture. In transformer we use this multi-head attention, and multi-head attention has two primary inputs. That's basically query and the key, and then you have a value that goes as an input. So that's a very brief explanation of this particular paper. And let's say, I mean, as in conclusion, I would say a different BERT, I mean, BERT is making a difference in terms of the the way we look at the documents, right? So earlier, let's say a term that was looking for, I mean, we are looking for that matches the term, and then it gives you the frequency, the highest frequency, having the documents having highest frequency of the terms gives you the output. But a BERT has introduced a little bit of sense or meaning or semantics in the way we search things, right? So this semantical understanding was not there with TF-IDF and the way this cosine similarity thing worked. So a semantic is basically extracting the meaning of the of the sentence. So it is not just the document that are more meaningful to the query, it is even the meaning of the query that is being feeded into the search engine, right? So we need to see both way, and then we get the final thing as an similarity of the query and the document, right? And then you give the best output out of that. So that way is definitely Google is making a difference. And and TwinBird and TinyBird, and there are multi other variants which are making it in a different way. Like let's say a query is again being embedded. So what we do in TwinBird is we embed the query, we embed the document, sorry, we embed the query, we embed a key. So that key is some kind of key term. So let's say somebody is searching for shoes, best shoes available in Amazon, right? So and some retailer, they have paid Amazon for some of these key terms, so if that is I mean, these key terms are basically externally fed in from the engine, and once that is matching, it will give you the shoes according to the user that's looking for. So it's like based on the ad sense, and and a set of like it could be billions of keywords that is being passed along with the query the user is searching for. Yeah, so search engine optimization works in similar fashion, but this is not looked at in the way BERT works, right? So we in BERT we do the same thing, but let's say if it is not incorporated with the search engines, it is not going to make that difference, right? So any questions so far?
Yeah, Suresh, this is good presentation. One quick question. But see, BERT is a very generic, right? But in a domain-specific search, it may not be the good one, right? It is very specific to in general search engines.
Absolutely, absolutely. I mean, if you see Google, right? So that's basically a general search engine, right? In that case, is Google is, I mean, BERT is really making a difference. But I mean, BERT is not meant for, I would say, specific things. It's a pre-trained language model, and pre-training needs a huge amount of data, and that's basically, let's say, you Wikipedia, if you take, right? So Wikipedia consists of all domain information. Now, a pre-trained language model which is trained on Wikipedia, which is
Yeah,
basically all the information, and we wanted to go in depth about a particular domain, right? So that is not expected. So
so have you tried the fine-tuning using BERT to a specific domain?
no, the challenge is we really don't have so much of data. I mean, it is very, I would say, it's not just that you have some dump of data available, but you need to curate it. You need to have a proper
No,
format
that
to feed it
no,
in.
that part clear. I know, I understand that, but they are just trying to understand. Have you tried fine-tuning using the transfer learning from the BERT? Just trying to understand.
We did with, let's say, clinical data. Okay, I did with all the clinical information that is available. So with that, it works, but I would still say that it needs
Mm-hmm.
more data and more specific information regarding that domain. Then it will work. It is not that it doesn't. It does work.
Okay.
So for
The
our
reason is
product team, we are
recently.
using BioBird. So
Okay.
BioBird is a
Yeah,
specialized
absolutely.
biological bird, and we are successfully using it in multiple NLP products in our product team.
Oh, good. That's what I was trying to understand. Yeah.
Yeah,
Because
yeah.
recently I was reading a paper. What they say that instead of fine-tuning the BERT model with a specific domain, you kind of right from scratch. You do with a small model, you get better accuracy and better performance. So I can
Absolutely,
share that
absolutely.
paper. Yeah, that was what I read 2-3 papers where they're saying that instead of doing transfer learning, you kind of you have with less data, small model, domain specific data, you start from scratch, but that gives better results. That's the reason I thought if you have tried, and but that was a paper, but I have not seen anyone practically doing it, showing it. Yeah.
No, clinical BERT and these applications like DistillBERT, right? So they are basically a filter of what BERT used to do. So in that way, DistillBERT, we have used actually DistillBERT for clinical data, and
Okay,
that's really doing good. Yeah.
okay, that's what I. Oh, good, thank you.
Yeah. All right. So I'll just quickly show you the paper. Um, so as we quickly discussed about these, I mean, I would say that there are like 40% of the pages detected as spam every day, and Google changes its algorithm on average 6 times a day, which is really a huge number and a bigger and never-ending task to be solved, which I really don't see that. I mean, I mean, how Google doesn't charge for any of the search that we are doing, right? And this is a huge amount of work that's being done, though they are earning from ads or a particular, that could be a different way of monetizing it. But let's say if we think of a specific search engine only for baby foods available all over the world, and or probably education specific, like somebody searching for a particular molecule and how that reacts to other molecules, right? So you, instead of reading a whole book, Bert is reading the book and it is giving you the specific answer that you are looking for, right? So that is something needs to be, like, I would say, to be implemented and to be seen in real world. So let's say the keyword, right, and in SEO, that how it works in a similar fashion, that you have a keyword, and then that goes as a matching, and then you see a query that comes in from the user, and then you find the ranked documents based on your keyword and the query, and that matches with the pages available in the web, and then you give the highest ranked documents as an output to the user, right? So that's how, I mean, we kind of changing or improving the way. And Google actually did this test, and they found that it has improved almost 7% of their search queries or search outputs in a better fashion, or the way we retrieve the results. And as per the paper overall, the best, this TwinBird model outperforms. They had a few of the experiments done with different models, with BERT large and BERT extra large. So they find that 3.7 to almost 0.42% of the searches becoming, I mean, that becomes a faster and gives a faster results on the output. So I had this one output here. So if you look at these particular results, so we see that two of the BERT where query and keyword are concatenated and encoded as whole, and efficiency of TwinBird, that is having 77 and 422 times faster. With TwinBird, the efficiency is even, so we have these I mean, let's say these two variants, and res and cos. So it's basically based on the cosine, and not using any cosine formula. So in that case, it is doing little bit better than what the residual formula is. So the based on residual network. So the keyword embeddings are generated in runtime, and yeah, as we know, in search engines. So this is how similarly this works, the TwinBird. And I don't have the code now, but I would like to as a future work, I would like to work with this TwinBird and see that how we can make the search results better. Okay, so that's all from my side. Let me know if you have any questions.
Okay, interesting session. Audience, any questions?
Google uses BERT, not variant of BERT.
So Indrajit, do you know for a fact that Google is already using BERT in search engine?
Google started using from October this year BERT
Yes.
in their search.
Oh, okay.
Yes.
They
Okay.
recently started.
So because BERT was from DeepMind, right? Or Google only?
No, Google.
Google.
So they are kind of using their own tech. Okay, got it.
Yeah.
So how do you see this GPT-3 and the new thing which has come out, and other things like ExcelNet? Or is BERT is still sort of the riding the wave in the
Yes, definitely. I mean, these variants are like, they have a little change over how the algorithm works, but the overall framework is same. I mean, let's say taking the tokens as in CLS tokens as an input, or
Mostly the transformer architecture is, so they are kind of,
that's
it was
constant.
yeah. Yes,
But
that's the
transformer
concept.
architecture,
Yes.
yeah, right.
And they use
Even
a lot of
I would
that's
say,
what
go ahead, please.
sorry, I was trying to say that GPT, they had it's a rich man's model where you use a lot of data and lot of GPU
Absolutely.
power, right? So that's what I can
Absolutely.
say. But the
Yep.
trend is more of a smaller models where you could deploy on the edge devices, right? Anywhere from your mobiles to anything. That's where the trend is, where I think GPT-3 will be
Correct.
like with Google, Facebook's kind of people, not for all small other companies.
Correct. Yeah. Yes, and that needs a millions of dollars
Yes.
to train.
And in enterprise applications, see, the ballgame is different, right? see the deployment, all this. I work for SAP, so we have seen that. My experience shows that all this looks very good academically, but in enterprises, it's really challenging. The problem is you want to have a domain labeled data, and that you won't get that easy, right? And there is, even if you get it also, and there is a lot of bias in that, and a lot of privacy, GDPR. There are many things. That's the reason. All these things looks nice at the outset, read academically, but still enterprise are really struggling to kind of use all these things and put into practice
Absolutely.
to specific applications.
Absolutely. We see this even with the Google, right? So they have implemented it, but they have millions of algorithms that's working for make the search better. And
Google is a general search engine. It's not a kind of an enterprise
no,
where
yeah. So
matters, right? Yeah.
yeah,
Privacy matters. Sorry. Yeah.
Correct. So I'm making the comparison in sense of the amount of work that needs to be done, and it is not easy actually. Even though if you have data and then you see still there are a lot of improvements needed for the search and the results that you get, right? So um, uh, so even though if we get or probably we create a synthetic data, right? It is not going to solve the real time problem.
Yeah. So I was
Suresh,
trying
to
to
augment
work on a
your
legal
point,
firm. Yeah, sure. Sorry.
so
Sorry, go ahead.
Suresh, I was just augmenting your point. So that is the precise problem we are solving or trying to solve with the product team, because there is a lot of good academic papers and research. Now, productizing it for actual business use is where a big gap exists in addition to a new research, of course. So in our product team, we are having to do a lot of churning and twisting to actually create products using the research, right? So it is taking a lot of turning and twisting. It's not so easy. Yes, I agree with you. Productizing
Yeah,
research
more
is not so easy, but that
I
is
feel like
exactly
more
what
the
we are
requirement of a
targeting.
label data. So Vishal, what I feel is that, more than anything, I feel the label data for a domain is
I mean, we
really
have been
important.
able to find data like in health and pharma, and we have been
Okay.
able to launch some products. We are doing current demos to potential customers in the product team, and we are seeing good feedback. And we
Oh,
are getting some custom requirements from potential customers, and we are actually in the process of actually adapting the currently deployed products to those. So, but it takes a lot of churning. It's not so easy.
yes.
Matching
I fully
research to
agree.
products remains a big challenge, and but we are able to make good progress in that, and our product team will attest to it. And if you have
Mhm.
seen our product, so but yes, it is taking a lot of churning. It's not so easy to launch a commercial grade product around the cutting edge research.
Yeah.
So it's just a long term, effort which has to go in product to actually do that. And I think we are making decent progress. We have launched some products,
Okay.
and now we are productizing it based on specific customer, customizing it based on specific customer requirements. And our potential
Okay.
customers whom we are talking to do feel that maybe yes, indeed, we can productionize it for them. So yes, it's not so easy. I do agree with you completely. And the larger the firm, the harder it is to do for them because their agility is limited. Like large companies have too many processes and too many,
Yeah.
checks and balances. So the innovation
Yeah. Standards and all
slows
the
down
stuff.
significantly. Yeah. But with us being a startup, it is easier to be more agile in the product side. And very quickly, we should be able to demonstrate some upcoming customers' deployments, hopefully.
So I myself, out of my own interest, I've been working on the legal work. Okay. So there was recently a paper also. Inderjit, I can share with you. Probably you can talk later also. There is something called legal bird. So I'm actually working off my own, trying to see how we can use
Sure.
all the legal documents. Something. Yeah. So that is
Mhm.
something which I am working office also same thing. But yes, this I'm just trying to
See,
play around.
this is what I mean I had started working with Bird from last year, so I see this. I mean, a very huge scope. I mean, I could not really see in the industry that where we can fit, but I really see that. Let's say there is a there's a huge document available for a product, and you really do not
Yeah.
have time to go through whole document or any legal document, as you say. You feed in whole thing to BERT, it will give you the answer without even training from scratch. If you train it from scratch, you get 95 or more than percentage accuracy from BERT. I have seen that. So
Yeah.
so this has a good potential.
Yes. Yeah. So yeah, BERT and it's all accessories around it. So many increasing layers. This all those things. People are doing the variation, but yes, I feel that once you have the annotated data of particular domain, I think and a good GPU system, you can do things. That is what I always feel. So, yeah. Yeah.
Yeah,
Thanks. I
absolutely.
think it was a good session. Yes, I agree with you.
Thank you. Thanks, Vivek.
Okay, thank you. So, any final questions, audience, or any comments, Indrajit? Okay, so in that case, thank you, Indrajit. Excellent presentation, and I look forward to your next sessions already. Uh, thank you, audience, for joining for our research day today. We had 3 papers, and we hope to repeat this maybe another couple of months down the line. But we toggle between a product showcase and a research showcase. So our next one will be a product showcase, signature event, maybe sometime in February by our product team, and then followed by another research showcase after that. So thank you all for joining today, and hope you have a good weekend. And these papers have been shared with our current members, and they'll also be posted on our research portal in the coming week. Thank you once again. Thank you to all our research presenters today, and thank you audience for joining. We'll see you later.
Thank you. Bye.